Hello, here's a video for Section 4.2. This is a big idea in differential equations. This is Laplace transform. I'll try to explain why that is. So here's the idea. So we start off with imagine we have our as our goal to solve this constant coefficient linear differential equation. So, well, with constant coefficients, I think I'm being a bit redundant here with the two constant coefficients, but whatever. Okay, such that, so we have this equation here, right? And then we have the initial conditions stated here. So here's our goal. So we're going to use this Laplace transform, right, to transform this problem into an algebraic problem, whatever that might mean, and we'll see that what that means later. Then we're going to solve the algebraic problem. Okay? Then we're going to use the inverse transformation to transform the solution back to the differential equation. I notice my picture is in a different shape than the one in the book, but the idea is that this big S here, think of that as a collection of these differential equations. We can send all of these questions over to these algebraic space. We solve our particular equation for the quantity x of s, as indicated in your book. And then we, that's this step here. And then we ship it back over to our space S, and that's our solution to our differential equation. And that's the idea. Now the big ingredient in this comes from Theorem 1. So here's Theorem 1 in the book, which I'm not going to prove for us today. But I would like to show you how you can use this one formula and sort of an idea, a principle similar to induction. I guess to prove the general formula in Theorem 2 in the book, we would use mathematical induction, but let's take a look to see what happens here. So if we use this formula, okay, then look what we can do. We can try to calculate the Laplace transform of the second derivative of some function y. Using this formula, that's equal to s times the Laplace transform of its antiderivative, or the first derivative, minus the first derivative valued at 0. Okay? Now continuing with this equation right here, we would get the second line. Okay? And solving just using good old-fashioned algebra, we get this, right? So now look, we get an expression for the second derivative, the Laplace transform of the second derivative in this way. Okay, well, we can play the same exact trick right here with the trying to find the Laplace transform of the third derivative of a function, and what we see is we get this expression, which we see right here. Okay, now if you look at Theorem 2 in the book, if you continue that process for higher order derivatives, you get Theorem 2 of the book. Okay? And that's the main ingredient in this section. So let's do an example. All right, so here we have a constant coefficient differential equation right here. Okay? Now, what we do is we basically, in this next line, here, let me stop right there. This next line, we take the Laplace transform of both sides of the equation, and using the fact that the Laplace transform is linear, a linear transformation, we can take the coefficient 8 out and the coefficient 15 out. All right, continuing in this way, using our Theorem 2, as I just illustrated above, we get this expression. Okay? And continuing on, notice how I'm going to evaluate the expression by plugging in the initial conditions, which I've indicated a second time right here. We finally get to our equation, and this is over in the sort of algebraic realm right here. I make this substitution just for our purposes. I want to let x be the Laplace transform of little x. Okay? And now I'm going to solve this equation for x. So basic algebra from your algebra class gets you to this point. Okay? And now we see why you learned the idea of partial fraction decomposition in your, say, Calculus 1 class or maybe in an algebra class. It's more or less, a large reason for that was for this very purpose. So we use partial fractions. Now this I want you to actually exhibit on your homework and on the test to actually do this part of it. But if you do that, you get a partial fraction decomposition of our x. The reason for that is that if you look on the right-hand side of this equal sign, these objects we can actually calculate the inverse Laplace transform of, which will give us small x, and that's what I've done here in the next section, or the next part here. So using the using the inverse Laplace transform, I see that little x is the inverse Laplace transform of the right-hand side of this equation. So here I'm using the fact that the inverse Laplace transform is a linear transformation to break it up to find the, that's why this coefficient comes in front. That's why this coefficient comes in front. And it's also why I can basically move the inverse Laplace transformation over the plus sign. That's the concept of linearity in play. Now, from our charts, we see that the inverse Laplace transform of 1 over s plus 3 is given as e to the minus 3x, and the inverse Laplace transform of 1 over s plus 5 is e to the minus 5 risen to the t power, I'm sorry. And that's how we solve these problems using Laplace transforms. It's a very elegant technique. It's another example. Okay, number 6 in the same section, 4.2, is this question here to try to solve this differential equation. So I will proceed exactly as I did in the previous example, taking Laplace transforms here, using the linearity here, and our theorem 2. Going here, I've used the initial conditions to simplify our expression. Here, I have used algebra techniques just simply to solve the equation for the Laplace transform of x. Here to here is quite a bit of work that you will need to show on your tests and on your homework. But that's, again, a reason for finding the partial fraction decomposition of such an animal is so that once we get it to this point, we can apply the inverse Laplace transforms and solve our differential equation, as I've done in the next parts. So here I write down that little x is that, the inverse Laplace transform. Here I'm using the linearity of the inverse Laplace transform to move the L inverses over there. And lo and behold, we have our solution. And I'm just looking at our table from section 4.1. So this right here should be a little x of t, of course, because it's back in this is the solution of the differential equation. So, okay, so enjoy this. It's a very beautiful part of mathematics and has motivated an enormous amount of study after its creation, and the techniques get more and more powerful. So thank you very much. Talk to you later. Bye-bye.